Lesson number 3, we're moving away now from the measures of central tendency. We're going to use those, so hopefully those are embedded now into your understanding.
You know and understand this.
Yeah, now we're going to start talking about something a little bit different, which is called the measures of dispersion. And we're starting in this lesson by once again looking at ungrouped or raw data. So how to handle just raw data on its own. Both by hand and using Excel.
So if sort of remember what central tendency means, or what it means to measure central tendency, we've got some different ways of measuring central tendency. It indicates either the central value, so like the middlemost point, which would be your median, or center point, or the value that's repeated the most often, the mode, or the mean, which is the average of all of your values, right? So we're looking, central tendency really is like a middling number, right? The middle value, the median, the mode, the mean, whatever. But if you had a huge range from your lowest to highest value, or a really small range from your lowest to highest value, you could still end up with the exact same median and the exact same mean.
And it doesn't, so basically what we're saying is that by measuring the center point or the center value of your data set, really it's only giving you one indication of what the data is like.
Yeah.
How spread out the data is another important piece of information.
That's right. And it's actually also called measures of spread or measures of dispersion. And it means the same thing. So you might see measures of spread, measures of dispersion used interchangeably, and it means the same thing. So let's see how that looks.
All right, so here we go. When we have ungrouped data, so raw data, measures of dispersion will describe how far individual data values have strayed or are away from the mean. So we can look at the individual value for how far is this data point, how far is that away from the mean?
Yeah.
And that is called
it's a deviation if you're just calculating
it's called the deviation. So for one point, how far does it deviate from the mean? Well, what we're going to do is we're going to take the individual deviations, and there's this special way of kind of averaging out all those deviations to talk about the deviation for the entire data set, which is known as the standard deviation.
And there are three measures of dispersion. So you know, measures of central tendency, mean, median, and mode. Measures of dispersion will include range, variance, and standard deviation. And we'll just talk about each one in turn. All
right. So through the use of an example, here's 2 dot plots. They each have a sample mean of approximately 54. How would we talk about the similarities and the differences between these 2 samples? Right? And why is it important to notice the difference?
Well, and we've been given that the mean for both is 54, so that's a similarity right there. We could guess that maybe even the median would be similar, right? Because it seems sort of symmetric, you know, going on left and right hand side of the mean. But the way that the data is behaving near the mean is very different. If you looked at the left side dot plot as being like a class, and they were averages, you know, maybe the average is 54, but you've got some people who were getting well below 20 and other people who were earning over 100, right, say. And then the dot plot on the right, well, just about everybody is clustered around 54. So the one on the right looks a little more consistent, or the data points are all kind of clustered or hanging out around the mean, whereas the one on the left, the data is more spread out away from the mean.
So that's exactly what we have written here, is that sample 1 is much more spread out, so it has a larger range. So really, if we're looking for variation or if we're looking for consistency, this is something that the mean alone can't tell us, which is why we need to go to these other measures of spread.
Yeah.
So range. Range is basically the simplest measure of dispersion, and we calculate it, and we've already looked at this a little bit.
Yeah.
It's calculated by taking the difference between the highest value and the lowest value of a data set. And we say that this is a very quick way to get a feel for how spread out the data is.
Yeah.
Right?
But because it depends on only 2 data points, if you have outliers, then they're going to be in there. Because if it's an outlier, it's at the end. It's either the high end or the low end. So your outliers, if you've got a few of them, will have a major effect on the range. If most of your data is clustered around the mean, but then you just have these couple of ones that are way out there, then the range isn't going to be the best measure of how spread out the bulk of your data is.
Exactly.
Okay, so that's the only trick about the range, is that it only uses 2 points. You could have 100,000 data points, but the range is calculated by just using 2.
Wow.
And that's a limitation,
Yeah.
right?
Very big limitation.
Yeah.
Variance then. Variance is a little bit different. The variance is a measure of dispersion that describes the relative distance between the data points and the mean of the data set. Okay? So the variance, basically what you do is you square each deviation. So how far away each data point is from the mean. You square it. And then you basically find the mean of those values. Mm-hmm. So a deviation is the difference between a data value x and the mean of the sample x bar, or the mean of the population mu. And so here we have these two formulas. Okay, we've got a population variance, just as we had a population mean.
Yeah.
And we have a sample variance, just as we had a sample mean.
Yeah.
For the most part, the types of things that you're going to see will have these two behaving very, very similar.
Yeah.
You just have to read very carefully when you're dealing with population variances. Mm-hmm. Your examples or your questions will make it very clear that this is a population.
Yeah, we'll say a population of students taken from this,
Yes.
Whatever. So you'll know when you read it whether it's a sample or a population. And note that with the formulas, they're very similar. For population variance, if you're wondering what that little symbol is, it's sigma squared, but it's the lowercase sigma instead of the uppercase sigma, which is the summation notation. So sigma squared is the sum of x minus mu all squared over capital N. Okay, so notice there's a couple of differences here. Whereas the sample variance, it's s squared. So instead of using the Greek letters, we're using just a lowercase s. And it's the sum of x minus x bar squared. And notice, though, that instead of just being over little n, it's over n minus 1. And that's because a sample can't have the same kind of variation as the whole population. You're always going to have, the population is by nature going to have far more variation in it than any sample you could grab. So the way that we compensate for that, if you take a fraction and you make the denominator just a tiny bit smaller, then you increase the value of that fraction, like when you do numerator divided by denominator. So if you had, 10 divided by 5 versus 10 divided by 4, for your numerator and denominator, you create a value that's slightly larger. And what that does is that just helps to compensate for the fact that your sample can never have the same kind of variety in it as your population would, and our variance is measuring those differences. So that denominator just compensates for the fact that your sample's not going to be as varied as your population. Okay, so notice those couple of little differences.
So now we come to standard deviation, which is kind of like the godfather of really talking about dispersion. Standard deviation is so important because it really comes into play in all kinds of statistics later on. So here it is. This is the godfather, or we can even say the godmother of all statistics.
Yep.
The standard deviation is simply the square root of the variance, right? It's more useful than the variance because the standard deviation is in the same units as the data set, right? Variance, everything was squared, so it's in units squared. The standard deviation is in the same units. So here we have the sample standard deviation, which you'll notice is exactly just the variance.
Yep.
But now we've taken the square root of it.
So instead of s squared, it's s.
Yeah.
Yep.
Now this is one little note, and it's all of these formulas that we're doing are for ungrouped data only. So
raw
this is
data.
for raw data.
Raw data.
This is not data that's been put into intervals. For that, you can pay attention to the next lesson.
Yeah.
So here's an example. Miss Hughes and Mr. Jackson were hired to wrangle dinosaurs from the field so that they could be tagged with laser beams.
Important work.
It is. It's crucial. Team managers, though, our bosses, tracked how many dinosaurs we were able to collect in each of the first 10 days on the job. At the end of the 10 days, the managers hired myself full-time because I collected an average of 53.7 dinosaurs per day. Unfortunately, however, Miss Hughes was let go.
Yeah.
She collected 53.6 dinosaurs on
average,
which was lower than what I collected.
Mm-hmm.
Did the managers make the right call?
We're going to find out. Because we know, now that we've listened to the first half of this lesson, that the average isn't everything, Mr. Jackson.
That's very true. And so we will see. We will see if the managers made the right decision.
All right.
Now here's day 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And whose data is this?
This is yours.
This is my data.
Yeah.
Okay, so here I have how many dinosaurs I caught on each day. And you will notice there are some days when I was particularly interested in working. Day 3, I was very motivated. Even day 9, I was pretty motivated. I think day 9, I was probably motivated because
near the end.
It was near the end.
You get that burst of energy
Yeah.
near the end.
But then there was other days, like the first day, I'm a slow starter, right? And then there's day 4, which I need frequent and constant breaks. And then day 10, it's close to the end. So what's the point? But basically, if you look at the data, you notice that okay, well, the range. We could basically say, okay, well, the high value is 102, the low value is 12. So what's the range of this data? 90 dinosaurs. So that's a significant range.
Mm-hmm.
Let's calculate the variance. And to do this, we've stepped this into I, and I. Okay?
I.
So what we need to do first is to calculate the deviation and then the square deviation. So for each one of these points, here on day 1, I caught 12 dinosaurs. Well, what's the deviation? How far away from the mean is that? And because I know what the mean is, the mean was given in the question.
54.7.
54.7. I can simply say
53.7? 53.7.
53.7.
Yeah.
It was 12 minus 53.7, which gives me minus 41.7. On day 2, 49 minus 53.7 is minus 4.7. And of course, I continue this pattern all the way down, filling out as I go.
Notice that some of these deviations are negative, and that means that the point from which the deviation was calculated was below your mean.
Yep.
And then the positive deviations mean that the point from which your deviation was calculated was above the mean.
Yep.
So you've got some negatives and some positives here. If you were to add them all up, it's possible you could end up with 0. Right? And that would imply that every point is on the mean, and that's not true. And this is where we square the deviation, in part to get rid of those negatives.
Yeah.
Right?
So we square the deviation, that's I, right here, and we sum them all up, okay? So basically the sum of my square deviations is 9,734.1.
That's the numerator.
That's
of
the
the
numerator
formulator,
of the
formula.
Yeah, so here's S squared. And S squared says we take the sum of the squared deviations and we divide it by n minus 1 because this is a sample. And so what I get then is 1,081.6.
And this means that on average, that any day of Mr. Jackson's is 1,081.6 squared dinosaurs away from the mean.
Yeah.
So notice how because variance is squared, that we're talking about square dinosaurs, which doesn't have as much value. And if you have a bunch of variances, then the bigger variances mean bigger spread, and the smaller variances mean smaller spread. But if we can make this like a certain number of dinosaurs away from the mean, instead of squared dinosaurs away from the mean, then that'll be more useful. And that's why
we can find the standard deviation, which is basically the square root of 1,081.6. Which happens to be 32.9.
And we've typed it in this way, equals SQRT bracket 1081.6, because that's how you'll type it in Excel.
Yeah.
Squirt.
And so the reality is that when you look at this, with a mean value of 53.7, my standard deviation, so the average deviation of this data set is 32.9 dinosaurs. So on any given day, if I catch an average of 53.7, my expected number of dinosaurs caught within one standard deviation could be 53.7 plus 32.9, or it could be 53.7 minus 32.9. So it kind of gives us an idea of how spread out that data is.
Yep.
32.9 is a pretty large number.
Compared to the mean of only 53.7. Yeah.
All right,
Yeah.
so let's move on. A large standard deviation indicates that the data points are pretty far from the mean. Small standard deviation indicates that they're clustered closely around the mean.
Mm-hmm.
So, is my standard deviation really that bad?
I think you should compare your standard deviation to my standard deviation.
Exactly.
Yeah.
So, sample mean here is 53.6.
It was a little smaller.
It was.
It was a little smaller.
And so now what we can do is now we have basically an empty chart.
So you fill this in your notes.
And so you're going to want to fill this in as we go.
Yeah.
So the range for Miss Hughes' values, she never caught quite as many as I did.
No.
She never had a 102 day.
No.
But 65 is the highest, 40 is the lowest. So her range is 25. So instantly we see that there's a big difference.
Yours was 90.
Mine was 90.
Yeah.
Mine was much more spread out. This is much smaller. So let's find the variance. And again, follow these steps. We want to calculate the deviation for each point, and then the square deviation for each point. We want to take the sum of that, and then divide by n minus 1. So here we go. We're going to take a look at the deviation for each of these.
So 41 minus 53.6, 55 minus 53.6, 55 minus 53.6, and so on. And again, notice that if the x value, if the data point is below the mean, then the deviation is negative because it's under. And if the x value is above the mean, then the deviation is positive, right? So now we're going to square all of these.
And again, we would just be putting the squared number into the calculator.
Yeah.
To arrive at a completed column.
Yep.
Now we need to sum these square deviations. So we take all of them and we add them up.
Yep. There's the numerator of the formula for variance, the sum of all the square deviations for all your points.
And so if we want to calculate the variance, is that we take the sum of the square deviation and we divide by n minus 1.
Because it's a
and
sample.
because there's 10 days, it's 10 minus 1. And so you're going to see right away that the variance is significantly lower than what mine was.
Yeah.
Your S squared value is 76.7. Again, this would be in units of dinosaurs squared, which doesn't make a lot of sense. So let's find the standard deviation. We take the square root of 76.7 and we end up with 8.8.
So what that tells us is that on average, each point is about 8.8 dinosaurs away from the mean. So that on any given day, plus or minus 1 standard deviation, it's going to be my mean either plus 8.8 or minus 8.8. And that's sort of what you could expect to find if you were to just take any day from my sample.
Yeah, exactly.
Yeah.
So did the managers hire the right person for the job? Why or why not? And so what you can say is, okay, well, here's a couple of little plots.
They look familiar.
Yes,
They're
they
the
do.
first ones we saw.
Yeah,
at
the
the
first
beginning
ones
of
that we saw. So here's mine right here, and here's Miss Hughes right here. And so what we can say is that my standard deviation was 32.9, a very large number because everything is spread out. Miss Hughes' standard deviation is 8.8, so much smaller. And so if the managers were looking for a worker who would have consistent performance, then they hired the wrong person. Because my dinosaur wrangling was very inconsistent. I had several days where I was quite low. I had a few days where I was quite high. And really in between, there was a few days, but there's not a lot of consistency here. If they were looking for a worker who's very capable of high performance, but not at a sustained rate, then they hired the right person. Yeah. Miss Hughes' data is much more consistent than mine is. It means that she goes out there and she gives it a lot every single day and she gets consistent results. I tend to give more effort but then take more frequent breaks. This is not a reflection of reality.
Only if we were dinosaur wrangling instead of teaching.
Exactly.
Yep.
So here's another example that we're going to use Excel to complete. Okay, but instead of stepping you through the use of Excel,
which you're familiar with
you're familiar with now, you know, you've been using Excel for a while, we're going to show you what we did. So we're going to pull up our completed table. But
To show you how it
here's
looks.
two students, Ruben and Dana. For the summer, they're doing some landscaping and they're laying patio stones. They recorded how many stones they can put down in place every single hour in an organized table. Okay, so which worker gets more stones put down during the first 6-hour day?
Let's see.
So if we add up how many stones Ruben lays down, he's got 236. And if we add up how many stones Dana puts down, she gets 246. So Dana works at a rate, and she puts down 246 stones. Ruben slightly less at 236. So Dana puts down 10 more stones over the course of the day.
Now, if you had to choose between hiring Ruben or hiring Dana, the question is that enough information to go by? Just the fact that she was able to lay 10 more stones. And some people might say yes, some people might say, I wonder though about their consistency. Maybe we can use standard deviation to find out.
Yeah, because if the case is that Dana lays, 246 stones in 2 hours, and then for the rest of the day she goes and sleeps, she might not be the person for the job. No, that's not quite the case because we can see the data here.
Yeah.
But we could certainly approximate that, and we could certainly imagine a case where that might happen. So which worker is more consistent on a per hour basis? So consistency can be evaluated by comparing the standard deviation of the two data sets. So we're going to use Excel to calculate their standard deviations. So here we just happen to have our Excel file already sitting here and done. And so what we've done in this case is that we've entered the hours 1, 2, 3, 4, 5, and 6 and the data.
The raw data for Ruben.
We've entered the hour for Dana and the raw data for Dana.
This should look familiar because you've done this by hand in your notes for Mr. Jackson and myself.
Yeah.
Okay. Yeah.
So here's the deviation, which we've labeled as x minus x bar. So now what we've done down here is we've actually taken the sum of this value, right? And we found the mean of this value. So that wasn't given to us in the problem, but here we've got the mean number of stones that Ruben lays down is 39.33333. The mean number of stones that Dana lays down is 41. So again, based on the mean, Dana is higher. Okay? So let's take a look at the deviation here. The deviation suggests that we take the value and we subtract it from the mean. And so we've simply done that. Now we've done that and we've used some absolute cell referencing because we don't want this to move around. We want the mean that's in this cell to stay permanent. So we've got some absolute cell referencing in here. We've done an autofill and we've brought that all the way down. Over here we've got the mean of the square deviation. So basically we've taken the square deviation, so this number, and we've simply squared it. And if you ever want to add an exponent, you can see right here we've got the little hat. And the hat is basically say, okay, take this cell, whatever's in this cell, and raise it to the power of 2. Okay? And so what we've got is we filled this down, and here we've taken the sum of this. So this is the sum of the square deviations.
Which is your numerator of your variance.
The variance then is the numerator divided by 5 because we had 6 hours to choose from. N minus 1 would be 5. And the standard deviation is the square root, SQRT, of this value right here. So Ruben's standard deviation, working through it, is 3.669, and the decimal goes on for a while. So about 3.7. Dana down here, very similar, much the same thing. All of her processes have been laid out. And so what we can do is we can simply take a look and say, oh yeah, everything here is pretty consistent. It's pretty much the same thing. And when we arrive at this, Dana's standard deviation is about 8.1. So Ruben is much more consistent than Dana with a value of 3.7 as opposed to a value of 8.1.
So what that means is that on average, Dana's data points or Dana's hourly performance strays about 8.1 stones from the mean. And Ruben's strays only about 3.7 stones from the mean.
Exactly. And so, again, this kind of just shows that standard deviation very often is a handy statistic to use if you want to describe a data set.